Okay. So last day we saw how to see colors. So now we will see how to change colors. So let's start with we have already presented this that color images are images in which you have three channels, red, green, and blue, and then you have three matrices of values. And these matrices of values, depending on how or what are their relative importance, they give rise to the different colors. So at the end, a color is nothing more than a vector. So this is how much intensity you have in the red, how much you have in the green, and in the blue. So a color is a vector. So if you think of the red, green, and blue vector space, so you would have how much red you need, how much green you need, how much blue. And this is a number, so those are three numbers. So you can represent that information with a vector. So in this particular example, you would need a lot of red, less green, and many less blue. So when you say, so here you have, when you say three numbers, let's go to the whiteboard. So when you have three numbers, so let's put some other numbers. So I have a color, let's say a color P that I will represent with, I don't know, let's say 7, 3, and 1. So what we are saying is I need 7 units, or I need to travel 7 units in the red direction, plus 3 units in the green direction, plus 1 unit in the blue direction. This is actually the same when you have a coordinate, let's say it is 7, 3, 1, and then what you're saying is I need travel 7 units in the EX direction, 3 in the EY, plus 1 in the EZ. And this is the vector 1, 0, 0. This is the vector 0, 1, 0. And this is the vector 0, 0, 1. So it is the same here. So these vectors here, these ones, are the unit vectors. So this is 1, 0, 0. But now in the red direction, it is not in the X direction. The meaning is red. And this will be 0, 1, 0. And this one will be 0, 0, 1. So it is the same. It is the vectors, the basis vectors, they are giving you directions, and then how much you are traveling in each one of those directions. So for the computer, a color is just a vector. Okay, good. So then, all this you already know. So with 8 bits, if each one of these numbers, these 184, 95, 12, if I represent them with integers of 8 bits, then the maximum value that I can have is 255. So it goes from 0 to 255. So you have 256 colors, different colors. And because you have 3 of those, you can represent up to 256 to the third power number of colors. So that is 16 million colors. So with 3 bytes, you can represent this many colors. Very good. Then we also said that for instance, when we print, we are using the cyan, magenta, and yellow axis. And now, if we think of these axes in the color cube, these are the orientation. So let's see. So let's think of the yellow axis. So the yellow axis is green and red. So it is a color. So any yellow color will be a vector such that it is of this form. So it has the same amount of green and red and no blue. So that means that if I represent here, let's say that this is red, this is green, this is blue, these are my unit axes, then this is a point here in the plane that has the coordinate GT. So they go along the diagonal. So this is yellow. All the yellow colors will be in this diagonal. Do you agree with that?
Are we all the times the axis expressed that way, like where on the x-axis, g on the y and b on the
No, no, you can represent anyway. So if I turn this down, the information is the same. Yeah. Any other question? No? Okay, so a green, so my yellow axis is this one. It is the one for which the red and green intensities are exactly the same. And the same applies to magenta and to cyan. So magenta will be red and blue, and in cyan it will be green and blue. So now you could define unit vectors in these directions. So you can, instead of using these coordinate bases, you can use these coordinate bases and reaching a vector here, reaching a point in this cube would be the same if I tell you the instructions in the red, green, and blue, or I give you the instructions in yellow, cyan, and magenta. So if I tell you a color, so let's go back to a general color. So we have some general color there. So let's put it even more general. So let's say that red, green, and blue will be this one. So I give you a coordinate in the red, green, and blue, and this coordinate, let's say it is some red, some green, some blue. These can be exactly the same color as some cyan, magenta, yellow. But now this is the same color, but in a different basis. So the numbers will not be the same, but the coloring will be the same. You see, so I tell you the instructions to go through the RGB unit vectors to get to that point, and I can find similar instructions, but now in a different coordinate basis. So you will reach the same point, but now using different numbers. Do you agree with that? Yeah. Very good. So no matter what the coordinate basis is, what is important is that a color is a vector, and then you can express that vector in whatever basis you want. So this is a representation of the same. So we have some particular vector here, given by red, green, and blue, and then the point has not changed, but I have to find different instructions to make you travel from the origin to that point, but now in the cyan, magenta, and yellow coordinate basis. So the coordinates will be different, but the point is the same. Okay, so now let's take our favorite image and let's play a little bit with it. So let's say that we have this original image, and you compute the histograms of the different bands. So red, green, and blue histograms, and we have also there the luminance histogram. And now you take the red band and you apply a gamma transformation by a factor 2. So gamma transformation, we already know, this one of these point transformations. And if you remember, what it did was shifting all the values up. So shifting the values up means that now all the red values, the other two channels stay the same, but all the red values will be shifted up, so the image will become more red. And if we apply with gamma equals 0.5, now we are shifting them down, and then it becomes less red. But less red means more cyan. Okay. Then we can do the same with gamma equal 2 in the green channel, so it becomes more green. Gamma equals 0.5, so it becomes less green, that means more magenta. And the same with the blue. Can make it more blue, or less blue, that means more yellow. Any question? Okay, so we already introduced this idea that all we need to represent a color is 3 numbers, so we can give them as the red, green, and blue, but also we can use this kind of encoding that is called luminance and chrominance in general, and the particular kind of chrominance, there are many, but here I'm showing A star chroma, B star chroma, but we don't care about those. The important thing is that the information has to, or colors have 2 pieces of information. One is luminance, that is how many photons are arriving from a point. The chrominance tells us about the wavelength of those photons, the wavelengths and the mixture of wavelengths of those photons. So luminance is how many, and this is which are the colors. So for representing the color, we only need 2 numbers. Because the whole, so traveling to a point in this vector space, you need 3 coordinates, that's all. So if you need 3 coordinates, and one of them is already giving you some piece of information, you only need 2 extra to get the colors. So the color is given by just 2 numbers. Okay, so one is how many photons are arriving, the other one is which is the nature, which is the frequency and the mixture of frequencies that you have in each one of those points. And we already said that somehow the brain has been shown to perceive images in that way. So it seems that our eyes sees in this red, green, and blue because we have receptors for this kind of light. We already, that is what we saw in the last lecture. But it seems that somehow the brain processes the information, paying more attention to what is how many photons are arriving and what is the color of those photons. But it seems to separate these 2 pieces of information. Okay, so this was the first attempt to try to organize colors in some sensible way. It was done by Maxwell, actually, same of the Maxwell's equations. Have you seen Maxwell's equations? Yeah, yeah, yeah. So the same guy tried to organize colors in some nice way with some rationale, and he already discovered that red, green, and blue somehow had some important roles. And we will not see this one, so Maxwell triangle, but we will encode it in a different way. So this different way will be based in this separation between brightness and chrominance. And somehow, yeah, all the information is here, but I think it will be nicer if we present it step by step. And there are many kind of separation of this brightness and chrominance, so this luminance and chrominance. So here you have a couple of them, HSL and HSV, but we have already presented also this one, luminance and chroma. There are many, okay, but they all separate into how many and what is the nature of those photons. Okay, good. So let's start with the color cube. So the color cube, you can see the origin is here. So this is the 0, point. And then we can look for all those colors that fulfill this equation. R plus D plus B is equal C. So this is the equation of a plane. So just a reminder of these things are. So let's say that you have this plane here, and this plane here is defined by a vector that is perpendicular to it. Okay, so let's call that vector u, and we have the coordinate x, y, z. So x, y, z represents any point in this space, and we wonder what is the equation of all the points such that they belong to this plane. So the equation of that is, I will write it in two ways. U x equals a constant. So the inner product between these two vectors has to be some specific value. And this is also the usual inner product definition is U transpose X. So C, this would be UX times X plus UY times Y plus UZ. This is C. So this is the equation of a plane. So if we look at this plane, this R plus G plus B equals C, that is the equation of a plane. So R and G and B are the coordinates. So this is X, Y, Z. UX, UY, UZ is 1, 1, 1. Okay. So this is a plane that is perpendicular to the direction 1, 1, 1. The direction 1, 1, 1 is this diagonal here in the cube. Okay. And this is the plane perpendicular to that direction when C is 255. Okay, so the origin is here, 0, 0, 0. This is the blue axis, the red axis, the green axis, and then the plane R plus C plus B is equal to 255. It has to go through these three corners, right? Because this corner is red, green, and blue, so it is 0, 0, 255. This one is 255, 0, 0. And this one is 0, 255, 0. Okay, so that plane has to go through those 3 points. Any question? No? Very good. So then, let's look at, for instance, this side of the cube. Okay, so let's look at only this side. So on this side, the origin is there. And this is the blue axis, this is the red axis. And then we look at the intersection between, so what is the equation of that plane? So that side is the feature that characterizes this side. So for all these points, the green is 0. That is the characteristic. So can have any red and blue, but green is 0 because green is in that direction. And this side has to have G equals 0. So if we now look for the R plus G plus B equal 255, but G is 0. So actually that gives you, if I have the intersection of two planes, so let's draw a second plane here. So I have the second plane, the intersection of these will be a line. So the intersection of two planes is a line, and that is what we are having here. So we are having first the plane R plus 3 plus B equals 255, and then we have the plane G equals 0. And we said that this is a plane because this is 1, 1, 1 times RGB equals 0, equal to 255. And this one is 0, 1, 0 RGB equals 0. So we have the intersection of two planes, and the intersection of planes has to be a line. Which line? This one. This is the line. This is the equation of line. Right? This is the line R plus B equals to 55. So how is the intersection? So how all the colors in that line look like. So all colors belonging to that line, all those colors are of the following form. Let's see. So let's say, yeah. So let's say it has a red component. The green component is 0 because of this. And the blue component is 255 minus I. Do you agree with that? Yeah. So this 255 minus I is from here. When G is equal 0, B is 255 minus I. And let's count how many degrees of freedom we have. So how many degrees of freedom we have? We have only 1 degree of freedom. So only you can change only the one thing, that is the red component. And that is why it is a line. This is a plane, because if I can solve for B, so let's solve for B and say B is equal to 255 minus R minus J. So if you give me R and J, then I can compute B. How many degrees of freedom do I have? I can change R, I can change G. But because I'm intersecting with another line, with another plane, now I cannot change G anymore. So that is why it becomes a line. So this one is a plane because I have 2 degrees of freedom. So in this plane, if you tell me what red and green values are, I can compute automatically blue. So I have 2 degrees of freedom. But in this line, now I have only 1 degree of freedom, and that is why it's a line. Okay, very good. And then I can change my constant. So let's say instead of 255, it is 384, let's say. So now I can compute, I can try to draw that plane, and the intersection of that plane with the color cube, it is this hexagon. So at every side, there is a different line of intersection, and the total figure is an hexagon. So it will give hexagons. So it will give hexagons for all the C's that are between these two values. So the 255 is easy to see why. And the 510 is a little bit more complicated, but it is two times 255. And if you are beyond 510, then again you are cutting with a, so your intersection with the color cube will be a triangle.
I'm not understanding the V constant.
The V constant?
Yes.
V is the value. You remember it was R plus T plus V divided by 3.
Okay. Yes.
Yeah. Yeah. Actually, it is here. So the value is R plus D plus V divided by 3. And because R plus D plus V is C, then V has to be C divided by 3. Very good. Then we can look at some other plane, for instance. Let's look at the plane G equals 0 again. So at this plane here again. And let's look at this line. So this line for this particular constant. So yeah, constant is 383. So it will be R plus D plus B equal to 383, but D is 0, so it is R plus B. Okay, so it is this line, and this line goes from, yeah, it is this mixture of colors. Okay? So points in this axis that are purely blue. So points here are purely blue. Here, points here are purely red. This axis is red, and this axis is blue. And this line is a mixture. So this axis is purely blue. This axis is purely red. and this is the origin. And we are looking at this line. Okay, any question? And we can look at the other side. So the other side, so this side is G equals 0. This side will be G equals 255. So now we look at the other side. On the other side, we are looking at this intersection here. So this intersection here. What do you see? Yeah. So now the origin is here. So the origin, this is the 0, 0 point. And then it is this intersection. And again, where is the purely? It is more difficult. So here you don't have purely red, purely blue, or purely anything because you are on the other side. To be pure, you need to start at the origin, but the origin is not contained. We are on the other side, so we don't have those axes. Okay, very good. And then you can compute all kind of intersections with red equal 255. Red equal 255 is this axis, is this plane, sorry. So we are looking at this line there, so on. Any question? No? Very good. So then let's look at the cube from this corner. And when we look at the cube from that corner, so the origin is again there. So we have the three unit colors or unit axes, red, green, and blue. So let's say that you have a particular color, R0, D0, B0, but it gives you this color here. And now we try to express it in some other way. And we want the value to be part of that representation. Okay, so we want the value. So the value, what is the value? So the value is R plus T plus V divided by 3. But we can have a vector in the diagonal. So this is that. Okay, so you have some value, and value times R, value times T, value times V. So that means that you have the three, so this V naught, no, as a vector, it has value, value, value. So it is value times 1, 1, 1. So that is, we have a vector that is along the diagonal and has not the length, but has value V. Okay, so we are at this point, and you may remember we said a long time ago, we said when some color has the same value 3 times, that means that that is a gray point. Okay, so this is a gray point. So we have chosen the gray point that has the same value as our color. Okay, so good. This point will be gray. Now, let's look at the plane of this form, R plus G plus V, that contains that gray point. Okay? It will be this plane. And then, so it is shown here, okay? So that plane. And now I have to tell you the instructions to reach this point. This point has not moved, so it stays fixed. So I can try to give you this instruction. So go to the plane, I tell you. Once you are in the gray point in that plane, you take this vector. So it will be a point that is this far from the gray point. But I have to tell you in which direction, because there is a whole circle of points that are at this distance. So I have to tell you in which direction. So the way to tell you the direction will be, okay, take the gray point. This plane will intersect the red axis at some point. So there is a naturally defined here. And now I will tell you the angle between this vector and this one. So I will tell you these three numbers. The value of the gray point. I will tell you what is the length of the vector that you have to add. And I will tell you the angle that you have to travel from this line to your point. And then I'm uniquely defining my color. So this is what is here. Okay, so let's see. We have the value. We have the value is this one. We have the length of this. And what is this vector? The vector is the difference between your color and my gray point. So this is this difference. And then I have to tell you the angle. So the angle is, okay, what is this point? This point is red. So if it is red, it has to be, it can be written as red times something. And what is this something? It is the value, not the value, but the sum of your R and G and B. But this point here is this one. So it is R plus G plus B times the red unit vector. And it is this vector. This vector is this one minus this. So it is this one minus this. And then I have to tell you the angle between S0, that is this one, and this vector. So if I tell you these three instructions, these three numbers, I can tell you the color.
Why do we use the red vector for the plane for the angle?
You have to choose one.
Okay, so
Yeah, actually, those are the differences between. I put it here. There are many choices. You have HSV, LHS, this one luminance and chroma, or so there are many. And the differences between those many is the different choices of white, red, or I'll tell you the differences in some other way. So yeah, there is no reason for choosing red, simply that for this one, for this HSV, we have chosen this convention red. And actually this HSV is not, so that the letters are not random. So V, we already understand it is for value. This S is for saturation. Saturation is how far you are from gray. So the farther you are from gray, the more saturated you are. If you are very close to gray, you are very little saturated. And the H is called hue, and hue is okay. This is difficult to define. Mathematically, this is okay. So it is this angle, but in Spanish it is called tonalidad. But what is tonalidad exactly? So there is no exact definition of hue. But mathematically there is. You have.
How do we know the direction of the angle?
It is always the same. So it is always the angle between this axis, this vector, and this one.
I mean, we can go in both ways for the angle.
No, it is this angle is always how do you call it? Counted clockwise. So you have to go from here to here. So that gives you a direction. So from this vector to this vector. So that gives you in this direction. Any other questions? Okay. So so more representations of the same idea. We are given this point in this plane. So now the origin is there. So you see there is no convention. So you turn your color cube depending on what you want to see. Okay. So you turn it the origin is now here. This is the vector, the color that we want to represent. And then you have that vector that you want to represent. That is the vector in the RGB coordinate. And then you have this line 1, 1, 1 that is full of gray values. And it goes from 0, 0, 0, that is black, to 1, 1, or 255, 255, 255, that is white. And then all colors in between in that line they are gray. And now you understand why they are a line, because this is a line because you have only 1 degree of freedom. So all the gray colors, they need to have the same value in the gray channels. So they have to be of the form VVV. So in VVV, you have only 1 degree of freedom. So it has to be a line. Yeah. So this was our color. This is our line. So this is the vector V0 that we mentioned before. Now I can measure what is this difference, S, that is the saturation. But the module of that is the saturation. So I have the vector V, the vector of the value, the vector of the saturation, and I have a line that goes from the value vector to the intersection of this plane with the red axis, that is this corner. So I have this blue vector, and I have to go from the blue vector to your color. So that gives you the hue. Okay, so HSV is value of hue saturation value. Okay, so I have to give you 3 instructions. And this is consistent with having 3 degrees of freedom. So we mentioned that idea here. So if a color is given by 3 numbers, doesn't matter if I tell you the 3 numbers in some coordinate, in the cyan, magenta, or yellow, or luminance or chrominance. I need 2 numbers for the chrominance. I have to tell you 3 numbers. I need 3 degrees of freedom to reach a point. And HSV has in particular chosen these 3 numbers: the value, the hue, and the saturation. Any question?
Can you go back to the first HSV?
First HSV.
Well, this one is, or for example, one.
Yeah.
Why do we use this kind of color mapping instead of less ways for hue and
So
visually?
this one here, no?
Yeah.
Yeah. So this is a luminance, value, hue, and saturation. So saturation is how far you are from gray. So you see this flower here is very far from gray, while the water is not so far from gray. So the saturation is easy to understand. The hue is more difficult to understand. It is an angle, so we cannot say.
Okay.
Somehow it is related to how close you are to red. So if the angle is 0, you are very close to red.
So the color map, it doesn't go like from green to green, like
It goes from red to cyan, is the opposite of red.
okay.
And then it goes back to red. So it is an angle. And the opposite of red is cyan. Okay, so there we are. So yeah, so if you give me a color, it is very easy to compute the HSV representation. So HSV is simply I have to construct this vector, and here I know everything. There is no I need to make a difficult calculation. I can do this calculation also very easily. This is this vector, this is this one. So this very easy calculation. And then again, this is an easy vector to construct. Measuring the angle is also easy. So all I have to say is the module of this one, the module of the second, and the angle between these two. So given a color, an RGB color, going to HSV is very easy. So then we can look at this R plus D plus B planes. So let's say that this is our color cube, and I will look for R plus D plus B equal 10. Okay, so equal B is 10. So C is 10 times 3. So R plus D plus B equals V times 3. Okay, because V is so small, it is this little intersection, triangle intersection there. Okay, so then you increase V to 21. Now it gets a little bit less dark, and less dark, and less dark, and less dark. Okay. And at some point, you cross this border of having 255, the constant being 55. Okay, so that is for V85. It is the last plane for which the intersection is a plane, is a triangle. Then you increase V a little bit more, and now it is an hexagon. So it is an hexagon with this funny shape. And then you keep increasing. So those are the intersections. Okay. And at some point, you are back again to triangles. And you keep increasing. And at some point, you are in this corner, and your intersection would be just a point that is white. Okay. Any question? No? Okay, so let's make a break. This slide is just a repetition of what we had before, but now with some formulas. So let's say that you are given, so we are going from RGB to HSV. So you are given this point, RG0, RGB0, and we have to compute all these vectors. So these vectors is the value vector. We compute C, that is the sum of the three, so it will be 1/3 of C. Then the module V0 is this thing, and the module is this one. So be careful with that. So you have to report the module. Okay, so the module is this thing. Then you compute the difference, the saturation vector is this one. And then you have to compute what is the module, the saturation vector, that is this. And this is just the same. And now the angle. And the angle is between, we said, the gray point and the red vector. Okay, so what is the red vector? Okay, so this red vector, this point here, has to be of the form C00. Because it has to be C, because it is in the same plane as your color point, and the sum of R plus D plus B is C. So this has to be C00 because it is red. And then minus V0, so it is this one. Okay, so this vector here is always this one. And this is the saturation vector, and then we have to measure the angle between the saturation vector and your X vector. And you have to go from X to S0. And here, somehow, this is a kind of simplified formula. This arc cosine of the inner product divided by the modulo of 2. This, you recognize this formula, right? You know how this came to be, no? Okay, so this is standard algebra. That is, okay, so let's say I have a couple of vectors. Let's say I have a couple of vectors. Let's call these vectors A and B, A and B. I want to measure the angle between the two. Then I know that the inner product between the two the inner product between the two will be the module of one times the module of the other times the cosine of the angle between the two, A and B. So now you solve for that. Solve for that. The cosine that it is the inner product between the two divided by the module. Then this is the cosine of the angle. So the cosine of the angle is the arc cosine, whose cosine is this one. And this is also written as cosine minus 1. Minus 1, not in the sense of 1 divided by cosine, but in the sense of inverse function of cosine. Okay, so yeah, very good. So this is to go from RGB to HSV. So we have seen this multiple times. Okay, yeah, that's all these. This guy is very repetitive. And this is also something that is sometimes done. That is, we can compute what is the maximum saturation you can have. So if you look for the point that can have the maximum saturation, it turns out that the maximum saturation is this one, 208. And then instead of reporting the saturation, so S0, you report the normalized saturation. So S0 divided by S minus. No? This is a number between 0 and 1. And again, this is some other kind of very small details. What happens if X is 0 and then the norm of X is 0? So in general, we don't care about all those details. And the same arc cosine is a kind of ambiguous instruction because of what you said. You can go in both ways. But that is the definition of Q is from X to S, and that is unique. So it is only the arc cosine is not unique, but you should look for some other way. Actually, the best way is this is something computational, but it is you know this function atan 2. Do you know this function? No? It is tell me the angle. So you are given a coordinate here. This is x, this is y, this is a point x, y. Atan 2 is tell me the angle such that this is sine. The sine is y. So not the sine. I'll put it. Okay, so let's say that in polar coordinates, it is r and theta. We know that this is r cosine theta, r sine theta. And then atan 2 would take y and x sideways. Right? It is looking for the theta such that it is consistent with this y and x. And there is only one. It is always going in this direction, always. So instead of using the atan 2 comes from r plus tangent, and 2 comes from the fact that you are given two values for that. Okay, so this is the best way of computing angles. But this is something of implementation. So we don't care about those small details of implementation. Any question? Okay, so we know how to go from RGB to HSV. And the important thing there is that RGB is not the only way of specifying. There are many other ways. All of them, they require three numbers because you have 3 degrees of freedom in the RGB space to define it. So if you have to tell instructions how to reach a point, you also always need 3 numbers because you have 3 degrees of freedom. Very good. And so we don't care. So it is, my claim here is that HSV is not the most important luminance and chrominance representation. It is one of them. It is relatively easy to see, and that is why we explain it. But it is not the only one, and not even the most important. It is important to break your mind and say, okay, RGB is not the only one. Okay, now we are given an HSV point. How do we go back to RGB? So let's say that you are given HSV. So if you are given HSV, that is a point somehow represented in this coordinate axis. So this coordinate axis is fixed with the plane. So do you remember these triangles that were the intersections of a plane with the color cube? So you have the triangle, and you put your coordinate system on the gray. So the origin of the gray of the coordinate system is at the gray point. So now let's define a few vectors. So the v vector is the one that is perpendicular to the plane. So okay, this is easy to define. It is 1, 1, 1. But in this coordinate system, thinking as if you were in the plane, how would you see v? You would see v as going up. So v in your coordinate system is 0, 0, 1. Okay, you have x, that is the point, that is the vector that goes from the gray to the red. But in your coordinate system, x is 1, 0, 0. And you have y. Y has to be perpendicular to these two. And you know, again, from standard coordinate systems, you can define any vector in this way. So, for instance, let's say that you have the standard coordinate system. This one. Now I am emphasizing the directions of the vectors. So you know that x times this cross product, y is z, y times z is x, and z times x is y. This you know, right? From physics, no? So we are applying this property. This we know, and then y has to be v times x. Okay, then we are given in this coordinate system, we are given hs and v. So what is our color in this coordinate system? So our color is a point that belongs to that plane. So if it belongs to that plane, the v component will be 0. Because if v component is different from 0, we are away from that plane. So in that coordinate system, the v has to be 0. And then, what are the other two? The other two is the saturation and the hue. But if this is x, and this is our point s, so this angle is the hue, and the saturation is the length of this vector. So actually, this is the polar coordinate of our color. So the polar coordinate is the radius times the cosine of the angle, the radius times the sine of the angle. So in the XYV coordinate system, the coordinate of the point is this one, is S cosine Q. So saturation cosine Q, saturation sine Q, and 0. So in that coordinate system will be this number times the unit vector in x, this number times the unit vector in y plus 0. Good. Very good. Then, yeah, this is the same space for this. Okay, but so I have that color, and that color in the HSV coordinate system is this one. In the RGB coordinate system is this one, but still I don't know which one this is because you gave me the HSV representation. What I'm looking for is the RGB representation. So I don't know what is RGB. But what you see, you recognize from here is that the same color, the same vector, has two representations. One in the RGB coordinate system, another one in the HSV coordinate system. Okay, good. So then let's look for the RGB. So yeah, this is saying in general the coordinates, these brackets, square brackets are the coordinates. So the coordinates in the RGB are different from the coordinates in the X, Y, V. Here it shouldn't be Z, it should be V. Okay, so then I can try the following. So the following. What if there must be some matrix? There must be some matrix that transform because these are coordinate systems. And if these are coordinate systems, then there must be some matrix that transforms colors in the XYV to colors in the RGB. And I have to find the columns of that matrix. Okay, so that's a matrix. Let's look for that matrix. And then let's see what happens. So the matrix times the coordinate. So it will be, what are the coordinates? So it will be the matrix times, this is the coordinate. And this will be the coordinate of x. So the expression of the unit vector x in the XYV coordinate system. And then the coefficient times the representation of y in the XYV and 0 times the representation of v in the YV. So now the coefficients go out and the matrix get in, and then what we have is the matrix times the coordinate x, so the expression of x in the XYV, but now we are going through A. So after multiplication, we are in the RGB space. So all this thing is the expression of x, this vector, the one going from gray to red, but now in the RGB, and the same here. So it is the expression of y, but now in the RGB, the expression of v, now in the RGB. Okay, so we know now how to construct, how to construct this matrix. This matrix has to be such that these coordinates, what is x in XYV? X in XYV is 1, 0, 0. What is y in XYV? Will be 0, 1, 0, and 0, 0, 1. So the columns of A has to be the expression of x in the RGB, expression of y in the RGB. And again, we have reasoned this, but you could know this from linear algebra in first year. Okay, so x, y, and v in the XYV coordinate system, they look like this: 1, 0, 0, 0, 1, 0, 0, 0, 1. So yeah, the columns of A are distinct. We've reasoned already that. Very good. Now, let's see. We have to find XYV in the RGB coordinate system. So XYV is V is very easy. It is 1, 1, 1. So it is that one, but it has to be unit. So the unit length. So the vector has to be divided by the norm of that vector. So if you compute now the norm of the whole thing, it is 1. Okay. Good. Now, what about x and y? Okay. X and y, you have here we will come to how we know x. It will be explained later, but once you know x, you automatically know y, because you know that v times x is y. So you multiply these two, which is that one. Okay, so how do we know x? How do we know x? It's on a slide, something. There was an explanation of x. Yeah. It is here, explanation of x. Okay, so x is perpendicular to b and has equal g components. Okay, so let's do that. Okay, so I know b. Okay, so b is 1 over the square root of 3, 1, 1, 1. Okay, good. Let's call this V0, V0, V0. Now, x is perpendicular to b. Okay, so if x is perpendicular to b, that means that x, let's call it, yeah, x r times v0 plus y r times v0 plus z using wrong notation. X green plus x blue v0 has to be 0 because they are perpendicular. Okay. And the other one is that x must be, it must have equal g and b components. Equal g and b components. That means that it has to be written as x red, x green, but then x green red again. So now, and there is another constraint, that is the norm of x has to be 1. So it has to be xr squared plus xe squared plus x3 squared has to be 1. And here you have two equations. So you have one equation here, another one equation there. This now you can write as xr, xd, sorry. So you have two equations with two unknowns. Your two unknowns are these two, xr and c. So you solve for it, and this is the solution. This one is the solution. And once we know b and x, simply you multiply, you have y. Very good. So then now we have the full matrix of this matrix is this one. For an example, it is clear you don't have to know these matrices by heart.
Let's go back to the formula.
Yeah. This one?
The ones you wrote, maybe the demonstration.
Okay. This one here. Yeah.
It's like GT.
Because we said it must have the same green and blue components. Okay. So you don't need to know all the formulas by heart and all the numbers and it. But you need to know the reason. The reason you need to know. Okay, so now we have a matrix. So it was complicated getting to this matrix, but once we have the matrix, you know that. But it is very easy to multiply because now you have the matrix. You simply have to multiply by the coefficients. So it was this coefficient, so S cosine H times the first column plus S sine H times the second column, right? I think so. And 0 times the third column. So it is very easy. So now you tell me the saturation and the hue. I simply have to multiply this thing and will give you the color in the RGB. So getting to the matrix was complicated, but once you know it, applying the matrix is trivial. And the main message here is colors are vectors, and then reporting a vector requires giving you 3 numbers. And if you change the coordinate axis, you must give a way to go from one coordinate axis to the other. Any question here? And then we have here very nice representations of all these ideas. So let's say that we have this plane. So R plus T plus B equals 384. Now we separate the 3 channels. And so the 3 channels are separated here. Actually, you recognize where the red axis is. So the red axis is here. The blue axis, the blue axis is here. The green axis is there. So those are the lines align. Yeah, this red, green, and blue. Okay. And then, yeah, so for instance, this point, let me see, this point here, or even this one, first green is this one. So this point here would need very little blue and almost no red. See, very little red. Then we can turn it into hue, value, saturation. So the value will be for all these colors, they all have the same value because they all belong to the same plane. Now the saturation is how far you are from the gray point. This point here is gray because it is in this 1-1-1 diagonal. And then this is gray, and the saturation is how far you are from the gray point. So these points are very saturated. These points, these colors here, they have very little saturation. And then the hue is the angle. So what is the angle going from red to your color? So all these points here, the hue is very small because the angle that you need is very small. And then as you turn around, you will need more higher angles. Okay. Any questions? No? So again, 3 numbers to represent a color. That's all. And then a different one. It is this hue. Sometimes it is colored in this way. So you saturate, then you represent the hue there. Okay, so now we can play with colors again. So we can do the following. We have our favorite image. Now I transform it into the hue HSV space. I multiply the saturation by 50% and go back to the color space. So if I you go back to the RGB, this is what you get. So it is more saturated than the original. See? And now all the channels have changed. So before we made the transformation, which only one channel changed, but now because we are changing the saturation, all the channels are changing at the same time, and you see it is more saturated. This one, so you can increase the saturation, or you can play with the hue. Now let's play with the hue. So the hue is an angle. So let's say that I add 60 degrees to my hue. Okay, so what happens? So let's go here. So let's say that you are given any point. Let's take this point here. So you add 60 degrees. So red becomes yellow, the yellow becomes green, the green becomes cyan, and so on. So now this is what is somehow explained here. So red becomes yellow, yellow becomes green, green becomes cyan. And it is taking the hue, adding 60 degrees and going back to the image space. And you can add 120 degrees, and then 180 degrees. 180 is what we call the negative. So you can compute negatives very easily. 140, 300, and if you add 360, you are back to the original. So this is same representation of. Okay, so now we will make a histogram of the hues. So a histogram of the hues. Here we have 0 degrees, 60 degrees, 120 degrees, but we have labeled them with the colors, so red, yellow, green, cyan, so on. So this was the original histogram, and then by adding 60 degrees or 120 or 180, so we have different ones. Any question? No? Fine. Okay, so we have.
I have a question.
Sure.
If you increase the saturation, why it is wrong? Like the colors moving down to the
Don't change.
yeah, like
They don't change.
like they don't change really. They are like small changes.
Maybe so if you go from here, so look at this one now. So has changed. You see? It's changed a lot. And actually you would expect more higher values because they have to be more saturated, so they have to be closer to the edges.
Yeah,
To the 155.
they're like no so much, no, like
They don't.
like o sea que no hay tantos como, o sea, que no hay muchos más que hay.
So the number of counts has to be the same as before, exactly, because it is the number of pixels.
Yeah.
So the total count has to be the same. But now what happens is that it is saturated. Actually, should be yeah. Here for the blue you see, and for the green, not for the red, but for the other two you see very easily. So you have these values here, the blue ones. Okay, you increase the saturation and they saturate.
Okay. I was saying maybe the red.
Any other question? No? Okay, so now let's play with colors in a different way. So let's say that we want to find a transformation such that we transform all colors at the same time following some pattern. So you have a vector. I is a vector. It is the color that you have at that point. You go through a transformation, and then J will be different colors. That is the meaning of that. Yeah, so let's see. So let's say that you have this original image, and somehow it has been degraded to any one of these versions. Okay, so this was the original, but you have an age. So you apply some transformation to it. Okay, so let's see. So you can apply two kinds of transformations. One is linear transformations or non-linear transformation. So linear transformation, matrix multiplication, it is so any linear transformation can be represented as a matrix multiplication. So you take the original color, you multiply by a matrix, you have the new one. And you might have some other non-linear transformations. So for instance, we already know the gamma correction. So you can apply the gamma correction, and it is a non-linear one. And the definition of linearity, so transformation is linear. Let's say that you have a couple of colors. You have color P0, P1. This is transformed into P0 prime through the transformation. This is transformed into P1 prime through the transformation. And transformation is linear if A P0 plus P1. So this is a color, this is a vector, this is another vector. I can perform this vector operation. So I transform this vector. So this is A P0 plus P1. It's the same A P0 prime plus B P0 P1 prime. So if this is fulfilled, the transformation is linear. For matrix multiplication, it is linear. For this one, it is non-linear. Oh, very good. Okay, very good. So then, for instance, we apply this transformation, say. So this transformation is just scaling only the red color, the red channel. You see the green and blue, they stay the same. So if we multiply this by this vector, the green and blue stay the same. And R0, by this scaling factor, it goes to R1. So you're just making it more red. Okay, so if you have something like 125, it goes to 175, the other two stays. So you are making it bigger in this direction. So from R0, you are going up. Very good. Then you can apply the scaling factor in green, you can apply the scaling factor in blue, and you can apply in the three of them. And in general, a linear transformation will be some full matrix. So if you look at these matrices, they have a lot of zeros. So a lot of zeros means the green and blue channels are not affecting the red. And so the output green is only affected by the input green. The output blue is only affected by the input blue. But if you have the full matrix, all channels, all input channels are affecting to all output channels. Okay, so you can apply linear transformation. And you can have a color in the input image, you multiply it, and you have your output color. And this is just a matrix multiplication. Okay, so let's say that I have an image. I have an image I multiply by some matrix. I go to J. So Rj is Ri multiplied by A. And then I have J, and I want to come back to I. So I can simply solve for that. So I can say Ri is A minus 1 Rj. So now, so going in this direction is A, going in this direction is A minus 1. This is the inverse of A. So let's say that final result, yeah, this one. So this is I, this is J. So let's say that this is the original image. You multiply by some matrix and you get J. But you don't have access to I anymore. So what you have is J. So can I restore and get I again? So you have an H image. Can you go back to the original one? And what you need are correspondences. So you need to say, okay, this color here, I want you to be this one. So you see the most important change is in the blue. So the blue channel, you are making it bigger. Okay, so the other two almost stay, and the blue channel you are making it bigger. And then you have to find some other point and say, okay, these are color. I want to also to increase the blue channel, but not as much as before. Then this one, I also want to change the blue channel. And you make correspondences. Okay, so you make a lot of correspondences. So now you have all of your correspondences. Let's go back to here. So you have a lot of correspondences. So you say this color J should, or this color J should go to this color I. Very good. And you have K, you have N correspondences left. So now let's think. Okay, so let's think of this problem. Okay, so I have, let's think of this. What time is it? Yeah, we have it. So let's say that I have color I1. This is my first color. I have color I2, color I n, and I have color J1, color J2, color J3. Very good. Then I know that for each one of those, R J1, for instance, this is A times RI1. So this is a vector equation. How many colors, how many numbers do I have in this vector? This is 3 times 1, right? I have 3 equations. And this is 3 times 3. So actually my unknowns are these ones. These are my unknowns. I have to solve for this one. So I may try, and I know that the same applies to all the other colors, right? So I have 9 unknowns. I have 9 unknowns. I have 3 equations. If you give me 3, let's put it with 3. You give me 3. You give me 3. I have a well-determined equation system. So I have 9 equations, 9 unknowns. I can solve for the 9 unknowns, right? But you are giving me more than 3 equations. And how is that called? An over-determined equation system. And in general, unless it is consistent, so there is no solution of an over-determined one. So you have to find the least square solution. Okay, so the least square solution is this one. So it is the one divided this one. Yeah. Let us write the least square solution. So the least square solution is some matrix that minimizes this. So for every color pair color term. So I have R, I. Minus, we are going from, this is there. This is there. This is there. So let's see what this is. So for every color I go through the transform and I get to the color J. And ideally, if the whole system is consistent, this difference will be zero for all colors, for all pairs. But in general, it will not be zero. But then what I want is that at least the norm of that is as small as possible. So this is what I want. Okay, then the solution is this one. So let us see how to reason the solution. So there is a long way between the two, but there is a simple reasoning to see why this makes a little bit of sense. Okay, so let's say that I put all the J colors as columns of a matrix. So this is a matrix with all the colors, J, okay? And each one of those has to be A times matrix, this is I. This is I. And again, this is a matrix with all the I colors, right? Okay, so let's call this matrix I. Let's call this matrix I. This is not the identity matrix. It is the colors of those. So the I colors, and this, let's call it the matrix A. So I want to solve for I, for A. So one possibility would be, okay, so what about this one? What do you think of this? J, I minus 1, A. Is it fine? Do you like that? Why not?
Because we don't know if it's the enough.
Because?
Because we don't know if the transformation is the same.
Yeah, the transformation is the same. It is same. This is a matrix. This is a matrix. This is a matrix. So I simply invert this matrix and I put it there. Fine? No? Yeah. Okay. Then let's think of the sizes of this thing. So we said, let's use right for the size. This is 3 times 3. What is the size of this matrix? So the columns are colors, so it has to be 3 times n. And this has to be 3 times n. Actually, this makes sense, no? 3 times 3 times 3 times n is 3 times n. So I'm inverting a matrix that is of size 3 times n. Can I do that? The inverse only exists for square matrices. So this is not a square. So in general, I cannot invert it. Okay, so I cannot do this. Let's put the sizes again. So this is 3 times n, 3 times n. This is 3 times 3, this is 3 times n again. So I will do something. I will multiply on the right by I transpose. Okay, so sorry. J I transpose. Okay, so let's put sizes again. So this is 3 times n. This is n times 3. This is 3 times 3. This is 3 times n. And this is n times 3. So this whole thing is 3 times 3, and this one is 3 times 3. So now I can invert this one. So this one can be inverted. So now it will be J I transpose I transpose minus 1. And let's put sizes again. So this whole thing is 3 times 3. And this one is also 3 times 3. So the matrix A is also 3 times 3. So this is consistent. Now what we have not shown is that this simple calculation, that is relatively simple, it is the one that minimizes this. So this one here is this one. Is the one that minimizes all those modules. We have not shown that. So this is what is in the slides. So in the slides, we are given, so here is, I was going from I to J, here he's going from J to I, it is the same. And then, yeah, we can, if you are given, so this is the same kind of equation as well. That formula, this formula is extremely important. It is called the pseudo inverse. Pseudo. That is very, very important. The one that we wrote before, J A minus 1 I, that we can do, but this would be the inverse, right? If we were allowed to do it, because we have only 3, then this would be the inverse. And this thing, you see, let me use some like color this one. So this is multiplying J, this is multiplying J. So this yellow thing is the pseudo inverse. Okay, so the formulas are the same. Different notation, but it is the same idea. Then this is the original, this is the age. You give me the correspondences. And at the end, if you give me only 3 pairs, this is what I recover, which is not bad. If you give me more mappings, so you have the original, the corrected one, it's not bad, but it is not good either. If with more different 3 mappings, you have something different. 3 mappings with 4 mappings. So this was the original, this is the correct. So the more mappings you give, the better you will be able to estimate the matrix A. That's it. So final message of today, colors are vectors. Anything that you can do with vectors is just changing the colors. Any question? Okay, so let's make a break. And we are back for we